In the previous video, we went through understanding the integrated rate law. We looked at the integrated rate law of a zero-order reaction and also a first-order reaction. Now, to pick it just from the first-order reaction, let's understand its integrated rate law. Now, we know that the rate for a first-order reaction is given by equilibrium constant and then times the concentration of the reactant to the power 1. That is the meaning of first order. Okay. We also know that rate is given by the change in concentration of the reactants divided by the change in time. Because we're talking about the reactants, we always put a negative there because reactants disappear. Well, because this is rate, this is also rate, we can equate these two, and so we're going to have negative dA divided by dt being equal to Ka. Now, at this point we can multiply. We don't want to see this in the denominator, so we can multiply by negative dt. The other thing is we don't want to say negative this side, so a negative and a negative will do away, so we're going to remain with dA being equal to this. Will go with that, and then what we are going to have now is Ka, and then there will be dt. Of course, the negative comes there. Now let's divide by A on both sides, the concentration of A. So that is going to give us 1 over the concentration of A, and then we have got dA being equal to negative, of course this will cancel, so I'll go to have negative K dt. I've written this for a reason, that is because dA is on itself, and so even A is going to, we'll just put it alone like that. That's why I've separated them with a 1. Then I'm going to introduce the integral on both sides. So we're going to have the integral of 1 over the concentration of A, and then the limits is the concentration of A at a certain time t, and then down you always put the lower limit, that is the initial concentration when the time is 0, and that should be equal to this side. Because we have got this is a constant, we'll bring it outside, and then I'll introduce the constant, the integral symbol, and then we are going to have the time t, and then here we are going to have 0, the time when we just started, so we consider that as 0, and then we have got dt. Okay, I left out dA here. Now whenever we want to integrate 1 over x with respect to x, this will always give natural log of x, as long as it is 1 over a number. 1 over a number integral will be the natural log of that same number in the denominator. And so this is going to give us the natural log. What we can see in the denominator is the concentration of A, and then we are going to show our lower limit and our upper limit. So the upper limit is the concentration of A at a certain time t, the lower limit is the initial concentration of A, and that should be equal to, we have got negative K. Now here we've got a 1, though we can't see it, and when we integrate a 1 we are going to get, because we're integrating a 1 with respect to t, so we're going to get a t, and then the limits, the upper limit is t, the lower limit is 0. Alright, now at this point we can progress and substitute in, of course the upper limit there is A at a certain time t. So where there is A, we're going to substitute the upper limit, and then where there is A again, we're going to put the lower limit. So that will be natural log of A at a certain time t minus natural log of A initially. This is the lower limit, as we can see, and that is going to be equal to negative K. Where there is t, we put the upper limit, which is t, minus where there is t, we put the lower limit, which is 0. Now that doesn't affect anything, so we just write it like that. Well, we can proceed at this point and take this portion on the other side, and so we're going to have natural log of a at a certain time t being equal to negative kt plus natural log of a initial concentration. And this should tell us that this is in the form y is equal to mx plus c, where c is this one, x is the time, k is the gradient, in this case it's negative, and then y is this one. So we can actually, if you are talking of a sketch of a diagram for this, a first order reaction, the x-axis there is time, and then on the y-axis there is the natural log of a. Okay, like that. So because the gradient is negative, this moves in this direction. That's the meaning of a negative gradient. Alright, so that is it. Well, having understood this, now we also need to understand the half-life of a first order reaction. Now, half-life is the time taken to complete for half of what was, for the concentration which was there initially to reduce by 2. Imagine you have got initial concentration of 2 molar for a reactant. After some time, let's say after 2 hours, it decreases to 10 molar. So you can see that it has gone from 10 to, from 20 to 10. That is half of its initial. So the half-life for this reaction is 2 hours. And so we are saying the concentration at a certain time, if it is equal to half the initial concentration, that is what we refer to as half-life. Now, just getting this reaction which we have here, we'll get it, and we're going to take this portion the other side. So we're going to remain with a natural log of a at a certain time t minus natural log of a initially, and that is going to be equal to negative kt. Anyway, what I've gotten is simply this stage which is here. Now, when you have got natural log subtracting, natural log of a minus natural log of b can also be written as natural log. What is starting will be a, and then the other one which is coming second is going to be b. It will be in the denominator. And so same with what we have on here. So we are going to have natural log. What is starting will be on top the concentration at a certain time, then divided by the initial concentration, and this should be equal to negative kt in that manner. So now when we want to remain with the value for t, remember we're interested in half-life, and that t is what is giving us half-life. We need to go on and divide by k, but well, we don't want to know the concentration after some time. We're only interested in the initial concentration. So using this one which is here, where there is at, we are going to substitute half initial concentration, and so this becomes natural log, where we can see this one we are going to substitute, and that is going to be 1 over 2 initial concentration, and then divided by initial concentration, and that is going to be equal to negative kt. Well, this is supposed to give us, this is the same thing when it is dividing. What are we going to have there in this case?